I found this list that goes over the 17 most important equations in the world, and I'd like to talk about it. And to make things a little more fun, we're gonna do a tier list and rank them on how important I think that they are. So let's get right into it. I've got a little tier list here set up, and we're just gonna go one by one, and I'm gonna explain what they are as I do them. Number one, we've got the calculus equation, which is from Isaac Newton. What this is used for is finding amounts, basically. And it calculates the area under a curve, and it introduced the concept of limits. Essentially, a limit is nearing infinity, and it's used like slopes. So if you have a slope and you're trying to find out what's underneath it, then you can use the slope formula and the area of a triangle to find that out. But if you've got a curve, then how do you do that? You essentially shorten it up so that you're finding columns in between each curve, but you're doing such small columns that it's a limit to infinity that you're finding under the curve. So calculus, pretty big one. I'm gonna go ahead and start off just with A. It really pushed forward math, so I'm gonna put it in A. The Black-Scholes equation is used in finance, and it's used to project options prices. It's not a law, it's just kind of an improved estimation. So in my opinion, that's going in D. It's cool, sure, I don't know. It's just kind of like, whatever, it's a good estimation tool. Next up, chaos theory. It's not that impressive in my opinion. I mean, yeah, it's cool because it helps describe the undescribable, you know. By that I mean it's used in determining like turbulent patterns and different things that are really unpredictable. However, it doesn't do that. We can't describe turbulence, and this is just kind of another one of those things that it's a step, which is cool, which is really cool, but it's not doing it. I'm gonna put that also down in D. Euler's formula for Polyhedra, I think, is a really simple one. What it describes is the relationship between vertices, edges, and faces of a polyhedra. Vertices are where edges meet, edges are the edge, and a face is the face. It's used in geometry and a lot of topography, which is really cool, but it's really basic, and in my opinion, it's alright. It's cool. I'm gonna put it in, let's put it in B for now. Fourier transforms are really important right now in machine learning. What they're doing is transcribing data that have complex functions such as images or sound, and it makes it accessible by a computer. It transforms that into data that computers can really read, and it's super important, and it's critical in a lot of computer science right now, including AI and machine learning. I don't think that's the most important thing in the world, but I think for what it is, you know, it's hugely pushing technology forward. So I'm gonna put it into A. I'm gonna put it above calculus. Information theory is also kind of related to the transmission of data. It allows people to transmit like radio or wireless communication, and it really optimizes how to encode and use that. So it's used in storage, it's used in encryption, it's used in wireless communication, and that's all super important, and I think that's had a big impact on our modern world, but not as much as Fourier transforms or calculus. So I'm gonna put it high B actually, and I'm gonna move Euler's formula for polyhedra down to C. I think that works. Law of gravity, law of attraction. That was dumb. I'm sorry. This is just the law of attraction between two bodies, and the force that is found between two bodies in the world. Not only is it between like planetary sciences, but it's also found in, you know, between me and you. there's an attraction, quite literally. I think that's really important to describe just our better understanding of the world, like it's a law, right? It's not just some formula. It is one of the few on this list that are a law, and I think that's really important. We're gonna give this guy the first S tier. Logarithms are important, but much less so. They help describe the exponential relationship between two things. So often it's used in basically anything that's graphed. So even like audio quality or earthquake or any other earth sciences, logarithms are a huge tool that are used in that sort of graphing. What it basically describes is to what exponent does this base number reach the other number. I'm gonna put it high B. I think that's okay. Maxwell's equations are used in electromagnetism, and they help in describing wireless communication and electric motors and magnetism. They've got a lot of application to modern day technology, and that is huge. Yeah, I'm just gonna put them in B. All right, the Navier-Stokes equation. It's used in fluid dynamics, and it describes how changes in pressure and velocity and temperature and, viscosity, a wide array of different variables have an effect on a lot of fluid dynamics properties. And they're used a lot in understanding weather patterns and a lot of different particle and wave movements, including like ocean currents. I think they're really similar in importance to logarithms in the way that it's just kind of helped describe different fluid dynamics. Logarithms have more applicable usage, so I'm gonna put this actually in C, and I'm gonna put this over Euler's formula for Polyhedra. Normal distribution, another goated one. It's not a law, but it is a really, really common occurrence, and I think to be able to describe that mathematically is really good. I think that normal distribution has a wide range of applications. What it is the bell curve. As you might have seen, I think that 3 Blue, 1 Brown, he's got a really good couple videos on normal distribution and how it's just so common throughout the natural world. Highly recommend you go check those out if you haven't before. I'm gonna put normal distribution in the low A, below calculus, but above logarithms. I think that's fair. Pythagoras Theorem, a squared plus b squared equals c squared. We all know this one. We were taught it back in years ago. This helps describe that the closest route between 2 points is a straight line. And I think that is just super applicable in like route navigation. This is widely used just by probably me on a daily basis. If I'm trying to get between two places, I want to take the fastest route there. Even though it's used in proofs primarily, I think this one is also really important. I'm gonna put this in the highest B. I don't think it's quite like on the same level as the law of gravity, nor is it as applicable nowadays for like Fourier transforms, calculus, or normal distribution, but I do think that it deserves a high spot and above logarithms. Relativity, this is another big one. This is Einstein's E equals mc squared, and what this has done is really described how space and time are more one thing, space-time, and how gravity isn't really a force. It's actually more of a curvature in space-time. I think this one's goated. It's used so much. I'm gonna put it under gravity though, because I think that relativity has more of an application to like astrophysics and pure math, rather than, it's not like I'm walking around and thinking about how relativity just happens. I am thinking about though how if I drop something it's gonna fall due to gravity. Next up, we've got Schrodinger's equation, which is used highly in quantum mathematics, and it's really closely related to the observation effect. In fact, I think it's actually the same thing. Even the mere observation of an experiment can change the outcome. The famous thought experiment is Schrodinger's cat with the Geiger counter in the box. You know, is the cat alive or is it dead? You don't know until you observe it. Much more real examples are with light. So if you're trying to measure light, even taking in that observation affects slightly, but affects the amount of light that is in the room. So this one is pretty important, I think, especially for like quantum computing and like pure math. So I'm gonna put it into A, but I'm gonna put it low A. I still think it's a little more important than like Pythagoras' theorem, even though, you know, that one's just iconic. We're moving along here. We got the second law of thermodynamics, which is entropy. It's talking about the law of conservation of energy and how in a closed system, if energy can't escape, then energy will become more chaotic. I think this is really important because it really has to do with fluid dynamics and with particle physics and with really a wide variety of applications, and it is a law of nature. As things progress, things become more chaotic, and that's just a proven law of our natural world. So I think that's really cool. I'm gonna put it up to S, but I'm actually even gonna put it over relativity. All right, the square root of -1, square root of -1. I remember being back in like middle school and I was like, oh yeah, the square root of -1 is I, and thinking I was so smart. This is dumb. I don't like this. You know, this is used a lot in like complex numbers and a lot in complex mapping. And primarily it's used in being able to help describe things that can't really be described by natural numbers or real integers. And it is often just able to help assist in pure math and stuff like that. Don't get me wrong, there is a lot of application for it when you're even talking about like Fourier Transforms. You're able to then compute some things that you might not really be able to understand otherwise, but really, in my opinion, figure out what you need to talk about. Don't have some placeholder. And I get that, you know, things push forward, but in the same way, it's kind of like chaos theory. So I'm gonna put it in D. This is dumb. We're on the last one. The wave equation is pretty important to talk about the relationship between particle and wave physics, and that is widely applicable in weather mapping, in light computation, in wave dynamics, just in general. And I think that this has a lot of application in our real world when describing, you know, sound and light and really how we perceive the world. It has been able to explain a lot of that, and I think that this also has some ties into string theory, which also helps explain just how the natural world works. And so I think for that reason, it is definitely a high B. I'm not gonna quite put it in A because it doesn't really have a lot of day-to-day application. You know I just said that it has a lot to do with like sound and light dynamics, but I don't know. I don't do wave equations when I'm trying to set up lighting. I know it is taken into consideration, and even if I'm not thinking about it, that is what's going on, but I'm gonna put it in high B. All right, and that is it. That is our tier list of the 17 most impactful equations that have ever existed. I feel pretty good about all of this. You've got highly applicable laws up in the top and like applicable equations down at A. You've got really famous and iconic equations in B. You've got less famous but widely used in C, and you've got things that are really more of just a step in the right direction in D, and I think all that makes a little sense. if you have any questions about all these, or if you enjoyed this, kind of one-off video, let me know down in the comments. Please subscribe to my channel. It means just so much to me to get the feedback and to help grow an audience. This is the paper that I used. It's by Ian Stewart, and I found it from user Bifler Lens on Reddit. Thank you for them, and thank you for watching all the way to the end of the video. See you next time. Bye.